My name is Alan Smith, and I work as a developer, trainer, mentor evangelist for Active Solution based in Stockholm, Sweden. I like to work with emerging technologies, so I've been spending a lot of time looking at the Microsoft Azure platform and exploring the new services that have been evolving on that platform. I'm now focusing a lot of time and energy looking at the artificial intelligence and machine learning technologies that are becoming available on the Azure platform. And I spent a lot of time looking at the custom vision service, as well as the cognitive services. And I'm also exploring the Azure ML functionality. I've been an MVP since 2005, starting out as a BizTalk MVP, then moving through the integration track. And I'm currently an Azure MVP. I do a lot of work with the community. For the past 7 or 8 years, I've been organising the Cloudburst conference. And last year, we organised the first AI Burst conference in Stockholm. As well as organising conferences, I like to present at conferences, which have typically mostly been around North Europe. But with so many virtual events, I've been involved more with events on a global scale. And I've also been involved with the Global Azure Bootcamp and the Global AI Bootcamp, mostly through the development of global hands-on labs that the attendees have been working with. And I host a YouTube channel at youtube.com/user/cloudcasts.
I'm Eva Pardi, software developer and data scientist. I've been an AI MVP since this year, February, and since that I'm involved in different community activities. For example, I was part of the organizer team of the Machine Learning Conference and the Global AI community events. I write articles and often speak about my investigations and projects at meetups, conferences, or other community events too. My aim is to save lives and support humanity with AI and data. You can find me on LinkedIn, Twitter, and Facebook too, but you might as well send me an email.
So I'm going to start the session by talking about reinforcement learning. I'll be talking quite a bit about the theory of reinforcement learning, and also demonstrating some of the experiments that I've been working with related to reinforcement learning. So I'll start out by looking at what separates reinforcement learning from other more traditional areas, such as supervised learning. In supervised learning, we typically start out with a large labelled dataset. And that dataset, for many cases, provides the features and the results that we're trying to predict for many of the data points. And we're going to be fitting a model to that existing data that can be then used to make predictions on other data items. With reinforcement learning, we don't have a dataset to start with. We're going to be using artificial intelligence to explore an environment. An environment is going to provide some kind of simulation or game that we can explore by making inputs and measuring the outputs. So it could be a physics simulation, or it could be a game. Anything that we can run repeated tests on with different parameters and examine the results. We're going to have some way to react with the environment. So the environment must be able to provide a state, which is a description of the environment. So if our environment was a lunar lander game, the state could be information, such as the altitude and the velocity of the lunar lander, a map of the terrain that we're going to be landing on, and information such as fuel and engine temperature, and the mass of the lunar lander. So the state is going to be a description of the environment at some point in time. We need to make changes to the environment, and we do this by taking actions. So continuing with the lunar lander example, an action could be to set the engine to a certain percentage of thrust, or to use side boosters to rotate the lunar lander or move it in a certain direction. So making an action on a specific environment will cause that environment to transition to a different state. And taking an action that moves the environment into a different state could have a positive or negative effect on that environment. So an environment can also provide a reward, which is typically a positive or negative number. So if the lunar lander crashes into the ground at a high velocity, or runs out of fuel, the reward could be a negative number. If the lunar lander lands very heavily, the reward could be a small positive number. And if it lands very gently, in the correct position, it could be a high positive number. So a reward is a way of being able to place a score or an evaluation on how well the algorithm has been able to react with the environment. In reinforcement learning, the algorithm that interacts with the environment is called an agent. The agent will be fed the current state of the environment. It will then examine this state and decide what action to take. And taking that action may result in a positive or negative reward. So the agent is going to read in the reward and the new state of the environment and make a decision on the next action to take. And we're going to run around this for a number of iterations. So in the lunar landing example, we'll start off with a lunar lander above the moon with a certain amount of fuel. And we'll run around the simulation until a lunar lander has crashed, run out of fuel, or landed successfully. So if we have a large number of agents that are interacting with the environment and taking decisions that are going to improve the reward, hopefully these agents should be able to learn how to react with these environments. When we're working with reinforcement learning, we often talk about the agents evolving in their environment. One way of thinking of this is considering the infinite monkey theorem. The infinite monkey theorem states if you have an infinite amount of monkeys in front of an infinite amount of typewriters, one of them will write the complete works of Shakespeare. All the others will just write regular expressions. However, when working with reinforcement learning, we don't have an infinite amount of processing power. So we use algorithms to help the agents to evolve within their environment. Supposing we had a finite number of monkeys, we could identify the monkeys that were getting closest to writing Shakespeare. We could then crossbreed and evolve those monkeys. And eventually, through evolution, we would have a monkey that could write Shakespeare. Well, in theory anyway. It's a lot easier to get this to work with numbers rather than monkeys. And one of the ways of doing this is by using a genetic algorithm. In a genetic algorithm, we have an initial population of agents. We then need some way of evaluating the agents. So we allow the agents to interact with the environment, and we use the reward as a way of being able to evaluate these agents. We can then perform a selection. We'll look at the best performing agents. And just like in genetics, we'll have numerical ways of being able to perform crossover and mutation to ensure that the next generation of agents has inherited properties from the most successful agents of the previous generation. We've also added some random mutation, which helps the agents to explore other aspects of the environment. So let's have a look at evolutionary learning in action. This scenario is very similar to the lunar landing scenario. However, it's a bit more modern. What we're going to be looking at is landing rocket boosters in a simplified scenario of the rocket boosters used by SpaceX. For the environment, I'm using Unity, which is a game development environment that provides a fairly good physics engine. The state of the environment is going to be the altitude and the speed of the rocket, and the amount of remaining fuel. The action that we can take is the amount of thrust that we generate from the rocket engine, and this will burn fuel and reduce the mass of the rocket. The reward that we will provide will be the landing speed of the rocket, and the aim of the simulation is to make this value as small as possible. In the first generation, we can see that all of the rockets crash and burn. In the second generation, a couple of the rockets managed to land successfully. And we're using a genetic algorithm to ensure that details from the agents that land successfully are utilised when we generate the next generation of algorithms. We're using some random variation as well to ensure that we get slightly different behaviour of all the members in the population, and this helps them to explore the environment and come up with a successful solution. We have 25 members in the population, and you can see that as the generations progress, more and more of these population members are getting successful at landing the rockets, until eventually all of the members of the population will be able to make a successful landing. So in the rocket booster example, I used a genetic algorithm. I started with an initial population of 25 rockets. And the rockets just used the engine thrust at random. We then performed an evaluation by simulating these 25 rockets in Unity. The selection involved taking the rockets with the lowest landing velocity. Even if all of them crashed, some of them will have crashed more softly than others. So we can select these best performing rockets. We can use crossover to generate a new generation of rockets that inherit from the previous generation, and then make a few random changes to the way that the rockets use thrust, and then perform another evaluation. We saw how this algorithm, over a number of generations, can evolve to rockets that can successfully land within that particular environment. Depending on the example, we may choose different ways of representing the state. I've mentioned that in a lunar lander game, the state is going to be mostly numeric, and contain floating point numbers, such as the altitude and the velocity of the lunar lander. With basic games, such as Pac-Man, because the screen is such low resolution and the graphics are so simple, we can actually use the pixels on the screen to represent the state of the game. And this is very versatile, because many different games, if they're using the same resolution, can represent their state in this way. So the same model could be used for Space Invaders, or Pole Position, or any of these basic arcade games. However, as gaming has evolved, the graphics have become more high resolution and more sophisticated. This is a screenshot from Forza Apex. We're actually driving a Lamborghini on the Top Gear test track. So if you've driven a car before, you'll understand what to do in this position. And you can see that we should be making a left turn here. However, the signal to noise ratio in the screenshot is very high. We've got camera flare, we've got trees, we've got grass, we've got some road cones. And it would be quite difficult for an algorithm to understand that we should be making this left turn. Because if we don't know what road cones are, you may think that the best option is to drive straight on. So in this case, it would be an advantage to process a screenshot of the game and reduce the noise on the input. So what I've done with Forza Apex is to take the screenshot, transpose the screenshot so it's a top-down view, and then use colour filtration to extract the driving line into a low-resolution bitmap. And this input contains a lot less data, and more importantly, a lot less noise, so it's much easier for the algorithm to make decisions based on this input. As well as understanding which direction the track goes in, we also want to be able to avoid other cars. So here I'm using object detection in the ASO Custom Vision service to train a neural network to be able to recognise cars in Forza Apex screenshots. Different games and simulations will also require different actions. Sometimes this can be done programmatically, if an API is available, or if we can interact programmatically with a simulation. In other cases, we may have to simulate the controls. Pac-Man in the Atari game simulation uses a simple Atari joystick, whereas a driving game may take floating point numbers for the steering, throttle and brakes that are going to provide the input to the car. We've discussed the rewards for the Lunar Lander game. For the bitmap-based arcade games, we could use the score for the game as the reward. When I was simulating Forza Apex, I was using the total distance driven before the car left the track as the reward. So in this game, the agents could evolve by being able to drive further down the track. So in the driver game example, I was taking screenshots of Forza Apex, processing those screenshots to produce a low-resolution image highlighting the driving line as the state. The agent would provide an input, and the reward would be how far that car has driven down the track. So let's take a look at how that agent evolved. The first few generations of agents will just make random inputs, which will result in lots of crashes. However, after a number of evolutions, we have an agent that can drive in a straight line along a straight piece of track. When we get to a slight right turn in the track, the agent makes a decision to turn left. However, after a few more generations, the agent learns to turn right, but makes too much of an input to the steering wheel. As the agent evolves throughout the generations, it starts learning to make the correct inputs for the steering, based on the position of the driver line in the image, and we see it progressively getting further and further down the track by making these inputs. However, after about 100 generations and 48 hours of evolution, the agent never successfully learnt how to get round the sharp left turn in the track. When we use a much simpler environment, in this case a simple 2D simulation of a driving game, using distance sensors on the front of the car to be able to detect the track boundaries, and a fairly simple neural network to control the steering of the car, we can see that the members of the population can evolve much quicker to be able to navigate the track in this environment. And by the time we get to generation 6, the agent is successfully able to drive around the track. I evolved that 2D simulation into a 3D simulation, and we used it at the Global AI Bootcamp. It was first held in December 2018. It allowed developers all around the world to join together in local events, which were part of a much bigger global event. I was responsible for developing the racing game. It allowed the attendees to either drive the track themselves or to train an artificial intelligence to drive the course. And we had a competition between the humans versus the AIs. You can see from the results that out of the top 10 drivers, 3 of these drivers, including the top driver, were artificial intelligence agents that had started out with no knowledge of driving and evolved over a number of generations to be able to successfully complete the lap. Which poses the question, how many neurons does it take to be a racing driver? However, when developing this solution, things didn't always go to plan. In this example, when the initial population was created, due to the random nature of the simulation, the car that drove the furthest distance was actually driving backwards. So this car went on to form the next generation, with more of the best performing cars in that generation achieving the highest distance by driving backwards. So this backwards driving gene then became inherent in the population and was passed down from generation to generation, with the descendants becoming better and better at being able to drive backwards round the racing track. Although this wasn't the desired behaviour, it's a really great demonstration of what we would call a false minimum in machine learning. This is the reason we include randomness in the mutation stages of a genetic algorithm. One thing that's important to remember when we're considering how algorithms can evolve to perform in a specific environment is the amount of prior knowledge that humans take for granted. In the driving game examples, most people will understand the concepts of driving a car before they play a driving game, and they'll be able to use that prior knowledge to be able to have a base level of competency within the game. This website provides a nice demonstration of how human prior knowledge can affect learning. It uses a simple platform game as an example, as many people will have familiarity with this type of game. You have the option of playing the original game, or many different variations of the game, which make the game more challenging if we're relying on prior knowledge. If we look at the original game, we can see that it's a basic platformer. And convention dictates that we're going to start at the bottom of the screen, and we're going to be the guy with a blue shirt. Also, the arrow keys will allow us to move left, move right, and jump. And I'm guessing that the aim of the game is to navigate up the screen by jumping on these platforms. There's a silver spiky thing there. I don't think I'm going to jump on that. That may prove to be painful. There's also some purple things. I think I'll jump over the purple thing. And there's a ladder that I can climb up. I can jump onto the next platform and jump over the next purple thing. Well, that wasn't too successful. Let's try again. Let's see what happens if I jump on one of the purple things. You can see that it disappears. Now I've learnt something in the game that can take me further. I can progress by jumping on the purple things. And getting to the top of the screen, I can see that there's a door and a key. So as I used to play Manic Miner on the Sinclair Spectrum when I was a kid, I know that you've got to get the key, and then progress to the door, and then open the door with a key. So that was fairly straightforward. We can play a different version of the game, with masked semantics. In this, I have to learn which is the main character by pressing the arrow keys, and we can see that it's this blue square at the bottom. But we've got a green block, and jumping on the green block is painful. We've also got these pink blocks, which are also painful to interact with. But I can jump on the pink blocks, and they will disappear. The red blocks appear to be ladders, and I can climb up the ladders to the top of the screen. If I go to the cyan block, nothing happens. But if I go to the pinkish orange block, and then to the cyan block, I can complete the level. The main reason I could do that is because I played the game before and had some prior knowledge of how the map would look. We can go to the hard mode, which demonstrates how a machine learning algorithm would see the environment. Here we can see that there is a blue colour block that moves with the arrow keys, but we've got very little visual clues as to what is a platform, what is a ladder, what is going to be a monster, and the location of the key and the door. We don't even know that there is a key and a door. We just know that navigating through this environment in a certain way will lead to a successful outcome. And this is the way that the algorithm will see the environment. In a driving game, for example, the algorithm will have no concept of a car, or gravity, or centrifugal force, or winning a race. It will just understand that making certain inputs into that environment is going to result in getting a better score, which will be the distance driven. When working with reinforcement learning in Azure ML, we're going to be using a common interface between the agents and the environments. And this common interface is going to be based on OpenAI Gym. OpenAI Gym is an open source initiative that was originally supported by Elon Musk, as well as a number of other developers who are passionate about reinforcement learning. OpenAI Gym provides a number of simulated environments that we can use, and a standard interface for being able to connect our agents to these environments. One of the basic problems is cart pole. Here we have an environment with a pole balanced on a cart. The state of this environment is the position of the cart and the angle of the pole. The action that we can take is to apply a force to the cart, moving it to the left or to the right. And the reward is going to be the amount of time that the agent can keep the pole upright and the cart within specific bounds. We also have 3D simulations, such as bipeds and quadrupeds. We can evolve these creatures to be able to walk, run, or climb over objects. We've also got a lunar lander simulation, where we can evolve an agent to land the spacecraft between the two flags. And also included in AI Gym is an emulation environment for the Atari 2600 and many of the cartridge games that were available in the early 80s. So let's take a look at a couple of examples of OpenAI Gym in action. I'm working in Visual Studio here, and I've generated a Python 3.7 environment for OpenAI Gym. You can see that I've installed the Gym package here. When I installed Gym with pip, it also installed all of the dependencies that I need. So it's quite easy to get Gym running in a Python environment. I have some very basic code here. What I'm doing is creating an environment based on the mountain car environment. I'm then resetting that environment and defining that the simulation will run for 5,000 steps. And for each step, I'm rendering the environment, sending a random action into the environment, and printing out details of the environment into the console application. So let's run this application. In the mountain car environment, we have a car that's got to reach the goal at the top of a mountain. The car doesn't have sufficient engine power to be able to drive up the mountain. So in order to reach the goal, it will have to repeatedly drive backwards and forwards to build up momentum to reach the top. And you can see that by making random movements, it's never reaching the goal, it's never getting a reward. But we can see the state being returned in terms of the car's position and velocity. In the cart pole example, I've implemented a simple genetic algorithm. And I'm going to run 10 generations with a population size of 10. We start out by creating a random population. We then iterate through the generations and evaluate each population member in the environment. We can then sort the population to place the ones with the highest fitness at the top. Then we can perform our crossover and mutation algorithms. So let's see how this example runs. We can see the animation of the cart pole simulation as we run through each member in the population. OpenAI Gym provides a common interface between agents and environments. And this allows us to have a number of different environments and a number of different agents, and rely on each agent being able to communicate with each environment. The interface provides an observation space, which allows the agent to read the state of the environment. There's an action space that allows the agent to send actions to the environment. Reset will reset the environment to its starting position. And we have the option of providing render functionality. that can provide an image depicting the environment that can be used to generate animations. If we want to provide our own simulation, we'll have to provide that simulation as a custom environment, which is a Python class which derives from the gym environment class. In the initialization, we're defining an action space and an observation space. And we're also providing methods for step, reset, and render. When working in Azure Machine Learning, we're going to be working in a distributed environment. And to make use of the OI Gym functionality in a distributed environment, we're going to be using Ray. Ray is another open source project that provides a framework for simplifying the building of distributed applications. And RLib, which is built on top of Ray, allows us to build systems for scalable and distributed reinforcement learning. If you want to explore some of the concepts in evolutionary learning, there's a number of great resources available. And links to those resources are available in the session description. The global AI community organises many AI-related events on a global basis. The in-person events are currently put on hold due to the pandemic. But when this has cleared up, there will be community events, hopefully in an area fairly close to you. The AI Talks provide a number of presentations, featuring AI developers from around the world. A good starting point for genetic algorithms is the coding train. This series of webcasts provides a very energetic presentation of the concepts of genetic algorithms. And this is where I got the concept of the Shakespearean monkeys from. It's used in one of the examples for being able to code up a generic algorithm to evolve text generation to produce a Shakespearean phrase. If you want to explore using OpenAI Gym in reinforcement learning, there's a great series of webcasts by Centdex. We start out with the basics of exploring how the mounting car example works, and look at how we can use different algorithms to be able to evolve agents in the OpenAI Gym environments. If you want to experiment with self-driving algorithms, it's best to use a simulator rather than a real car. And Carla provides a great simulation environment for working with self-driving algorithms. The environment is developed in Unity, but there's a Python API that allows you to connect to the environment. The vehicles will provide LiDAR, object detection, distance detection, and various other functionality. And because it's built on Unity, it provides some great physics and a nice visual environment to work with. Another game that provides an API that we can program against for evolutionary learning is StarCraft. It provides a very challenging environment for being able to develop evolutionary learning algorithms. And again, for the StarCraft AIs, Centdex has also provided a great series of webcasts on this.
Thank you, Alan, for the introduction to reinforcement learning. It was really interesting to see all the projects you have been working on. I'm so excited to tell you about how Microsoft Research worked together with Ninja Theory on Project Paideia, which applies reinforcement learning on multiple agents. Microsoft made an amazing history in machine learning and artificial intelligence, applying machine learning to improve many of their products and services, such as for the suggestions made in the Office services. The approach of reinforcement learning became very popular in the recent years, since these game agents perform complex tasks very well, causing real breakthroughs in the field. There are many use cases in the world which uses this technology in the areas such as robotics, chemistry, education, and a lot more. The cool thing about a gaming situation is that the behavior of the agent is trained under the pressure of the game. Think of a character or a bot in a game. It has to understand the state of the game. Where are the players? Then based on this observation, it should make a decision based on the situation of the game. For example, it could learn what to do when it's being attacked, or how to behave in order to reach a specific goal. Microsoft proudly announced the preview of reinforcement learning on Azure Machine Learning at Build 2020. The new reinforcement learning support in Azure Machine Learning Services provides scalability while training to CPU or GPU-enabled virtual machines with machine learning compute clusters that can automatically provision, manage, and scale these virtual machines. You can use single agent or multi-agent reinforcement learning for your training scenarios. You can use different gaming environments, for example, OpenAI Gym. You can build your models with TensorFlow and PyTorch deep learning frameworks, and it supports ONNX 2. You can also track your experiments and monitor the runs. Azure provides numerous AI solutions to build, run, and grow your games. Use it to accelerate your games with AI and machine learning to provide more realistic worlds and challenges for your players. If you want to get started with reinforcement learning in gaming, check out the sample notebooks which you can find if you follow the link in the bottom of this slide, and train an agent, for example, to navigate a lava maze in Minecraft using Azure Machine Learning, which uses single agent reinforcement learning. The goal of this agent is to reach the blue tiles while navigating through this maze by walking only on solid tiles. The agent might fall into the lava, in which case it has to start it over. Since the maps are generated randomly, the agent also has to learn how to generalize and adapt. Now, let's take a look into an example of how multiple agents can be trained with Azure Machine Learning in a simple gaming environment. Microsoft Research worked together with Ninja Theory to explore new possibilities of reinforcement learning in gaming. The aim of the research is not to build an agent that is able to beat humans, just like the famous chess agent, but to provide game developers tools to make them able to apply reinforcement learning while building exciting games for their players. Project Paideia has been announced on the 3rd of August at GamesTech Live, and the state-of-the-art AI agents use Bleeding Edge as a research environment. So, in this session, we use the following situation. The blue circles are the agents, and they start spreading around and observe their environment while finding the landmarks that are shown as black circles. They get rewarded if they find the landmarks without overlapping while spreading around. For this, we use OpenAI Gym's particle environment within Azure Machine Learning. Now I'm going to switch to the demo and show you how does this work in a real coding environment using Azure Machine Learning Studio and the Azure Notebooks. So I have already switched over to my Azure portal, and to see this Azure portal you will need an Azure subscription. Then you also need a resource group and a machine learning workspace with a computation cluster in the resource group. And I have already created a resource group here. But if you want, you can create a resource group as well by going to the resource groups and click create. And then all you have to specify is a name and the region for the resource group. And then you can also create a machine learning workspace by go to create new resource and say machine learning. And then you click create. Then you define a resource group and then specify a name. And also you can change the region to wherever you prefer. And then just create. But since the machine learning workspace is also created for us already, you can just go after it is deployed, you can click on it, and then launch the studio from here. When you arrive to the studio, this is the view you see. You can choose to work with notebooks and create your own code and build your own models and experiments. You can choose to work with automated machine learning, where you automatically train and tune your models, and you also get the best fitting model for your scenario. And then you can use the designer to use the drag and drop interface, where you can prepare your data and deploy your models as well. So now we need a compute target. So we go to the compute menu, and you can see I have already one that we are going to use today, but you can go and click create. And I would suggest to go with GPU for this scenario. And you can choose whatever size you prefer. And then just go next. And then you define a name. And then you click create. Now I won't create a new one because we have one already. So I just go back and go to our notebooks. So the notebook environment looks maybe familiar because if you have coded with Python, you might have used these IPython notebooks or the Azure notebooks as well. It also has a similar folder system, and you can also write your own code in here. So what I wanted to show you quickly is this files folder because it's really important. The files that are in this folder can be found on my GitHub account, and you can go to GitHub per example, and then there is the folder called reinforcement learning, and inside that, in the files menu, you can find all the Python files that you want to use for this one. All right, let's move back to our main folder, and I opened up the particle Python notebook, and then let's write some code. So the cool thing about these notebooks is that all the tools that we want to use are already installed for us. So you just maybe want to upgrade your environment and then you're ready to use it. First, we return the SDK version for our Azure Machine Learning. This is quite handy in case you need to do some debugging. It is also a good idea to define which Azure tenant you want to use, so you can specify it with the use of the following code. And to find the tenant ID, you can just go back to the Azure portal and find it at the tenant properties. All right, now it is time to connect to the workspace. You can use configuration, or you can specify it by defining the name of the workspace, the subscription ID, and the name of the resource group. And if you want to figure out your subscription ID, you can also go and take a look at the subscriptions menu on the Azure portal where you can find details. If the connection was successful, then it will return the details of the workspace here. The next step is to create a new experiment, which will enable us to monitor the run. And as parameters, we pass the workspace that we just connected to, and we also specify the name of the experiment, which will be particle multi-agent. The next step is to create a cluster where the training is going to run. So I specify the name here, that is CPU CLD3. And it is going to first look around in the system whether this cluster already generated. And if it is, then it is going to say, yes, I found a compute target, so I'm going to use it. And if it is in a state that it is not available or stopped or whatever, then it is going to return you that information as well. Otherwise, if the cluster is not generated yet, it is going to create a new one. For this, we have to specify also what size we want to have of this compute target, and we specify the number of nodes too. Here we specify that the 1 is the maximum number of nodes. The good thing about this cluster is that it will scale down when it is not used, and you are welcome to increase the nodes as well if you plan to run more than one experiment on this cluster. And when the cluster is ready to use, this code will return that either the cluster is created or that it has found an existing one and it is going to use it. So we are going to use a customized Docker image where all the necessary software and Python packages are installed. The configuration for the training run is defined with the environment class. And since we also want videos as a result about the different runs of the particles, we need to set the interpreter path too. For example, you set that it has to be this size, and other extensions information can be specified here too. For training, we are going to use the multi-agent deep deterministic policy gradient, or the MADDPG algorithm, and as the name suggests, it will be able to train many agents in the same time. If the training runs over 3 hours, it will automatically stop. And we have to initialize reinforcement learning estimator, also with different parameters. The entry script is going to be this Python file that we are working with right now. And the source directory with all the other Python files to use are found in the files folder. We also specify some parameters. For example, what scenario to use. We're going to use the simple spread scenario. And the final reward is set to -400. So while the reinforcement learning training is running, then when it is reaching the -400 reward, then it is going to stop automatically. We also define that the CPU cluster which is generated should be used, and that the environment is the environment that we have initialized in the previous step. Finally, we also want to see some run details about the experiment while it's running, and the button is available to navigate you to these run details thanks to this line of code. And if you go click on the run details here, then a new page is opening up like that. And go to child runs, click on this one. And if you go to outputs and logs, it will navigate you immediately to the driver log, where you can see each trials, what was the reward in the end of that specific trial. And if you scroll back, you can see the previous runs as well. And I also know that it's not easy to walk through and see each of the trials one by one. Instead, in the next line of the next part of the code, you can generate a tensor board, which provides you a link. If you follow that link, you can go and take a look at your tensor board, where you can see all the different run details about your experiment, all the information in live while the experiment is running. I think it's really useful because you can follow how did it change. And it, as you can see, it refreshes itself automatically. The evaluation of the training is really important, and it is possible to reach videos about the different iterations. And this code is going to generate these videos. And then this one is going to download them and then displays it within the notebook. Look at this. So here you can see each of the runs, the whole video about the experiment, as the particles trying to find their path without colliding. You should run these codes, the tensor board and the video one, right after you start the training in order to see the videos and the tensor board correctly while the training is happening. These videos that are generated here, that you can see here, they're not running away anywhere. You can reach them if you go back to the run details and go to logs and then videos. And then here you can see all of them. And sadly, you cannot see it, and you can see it is refreshing immediately if something new is added. So you can download the video that it generates. You sadly cannot see it within the studio, but you can open it up like that, and then it is going to play it for you. See, they are almost there. They are going on the right path. All right. If you want to find some more details, you can go and see the updated information and content at my blog post that you can find at codewitheve.azurewebsites.net. As you can see, when you use reinforcement learning in Azure Machine Learning, you can easily monitor each iterations and see all the training results live while the experiment is running. If you want to read more, see these resources: blog posts, articles, videos, and code samples from the engineers of Project Pydia. I want to thank you for your attention. I hope you find this session beneficial when you build your next game. I can't wait to see what you come up with. It was a great honor to be one of the speakers of Data Platform Summit. Thank you.